Good morning, students. I would like to continue the topic of yesterday's electrochemistry. So, we are discussing the chapter under electrochemical cell. We completed electrolytic cell uh, and we are under electrochemical cell, right? See here, this is what I have completed yesterday in the last class, electrolytic cell, right? An electrolytic cell, anode, cathode, anode oxidation, cathode reduction, right? And I explained that there are two different cells in the electrochemistry, electrolytic cell and electrochemical cell, right? Okay, we will continue electrochemical cell. Actually, I have completed even this, just it's a repetition for you. Electrochemical cell is the one in which chemical energy is converted into electrical energy. Okay, and therefore and this is called as your electrochemical cell or galvanic cell or voltaic cell. Any one is one at the same, the words wherever you find. And Daniel cell is one of the example of your electrochemical cell. Even Daniel cell also works on the same principle, right? So working of this electrochemical cell, what I said that in one beaker zinc sulfate electrolyte is taken and zinc electrode is taken or dipped into it, and into another beaker copper sulfate electrolyte is taken and copper electrode is dipped into it, right? And connecting to those two beakers a inverted bent tube which is filled with agar agar and KCl solution. Agar agar is a gel like, it will not interact with these two beakers chemically inert, right? Just to electric to maintain neutrality, to balance these ions, it is going to be maintained, kept here, the salt bridge. Okay, and this zinc onto which oxidation takes place I call anode, and onto the cathode which reduction takes place I call uh, cathode, right? Copper reduction takes place, therefore cathode I said. As see here, when these two are connected through a metallic wire like this, and then the reaction starts. What is that? Zinc rod is going to do, convert into, I mean, zinc atoms are converting into zinc ions and enter into this solution, zinc as zinc plus 2. So the two electrons which are relieved at this electrode will pass through this metallic wire through this and will be given to this copper rod, that is cathode. So when this is taking these two electrons, here copper 2 plus which are present will be coming near to this electrode and takes those two electrons and will be converted into copper atoms. Copper plus 2 which are present in this solution will be converted into copper plus 2 atoms, copper atoms, and will be deposited on this rod as pure copper. Whereas in this zinc rod, I mean zinc atoms are converting and donated into the solution as zinc plus 2. So as electrons are moving, actually we call these two reactions as half cells or half reactions. Here oxidation takes place, therefore oxidation half reaction, and here reduction takes place, therefore this is called reduction half reaction or half cells. Combining these both, full cell we call cell reaction. Okay, so here electrons are moving from here to here, therefore as electrons are moving from generated at this anode and moving from here, this anode is kept as a negative terminal, named as negative terminal, whereas cathode is accepting electrons and cations are coming near to it, or whatever the electron, this is given as the positive terminal. This positive negative symbol, nothing to do, just to remember for you. If you forget, it's okay, but this is completely reverse from that of your electrolytic cell. Whereas in electrolytic cell we kept anode as positive terminal and cathode as negative terminal, because in electrolytic cell battery is given from the external, that is external source is supplied to the cell, where electrons, I mean negative terminal is connected to the cathode, therefore cathode is named as negative terminal. But whereas in electrochemical cell, electrons are generating here and passing from here, anode is termed as or negative terminal, that's it. But the reactions are same, there also anode oxidation only, cathode reduction only, here also cathode reduction and anode oxidation only. Please make a note, in reaction there is no change, but only the naming these terminals positive negative are changes from electrolytic cell to electrochemical cell. Okay, so here, as electrons are given by the zinc and converting into zinc plus 2. See here, for example, you may think that, okay, zinc this side is kept, that's why electrons are moving from here to here. Let us keep copper rod this side and zinc rod this side. You do whatever. Electrons definitely from move zinc rod to electron only, copper only, because zinc has more ease to donate electrons than copper. Copper has more ease to accept electrons when we compare these two. So this may be due to, you can compare, this may be due to their electronic configuration or atomic size or whatever, right? The simply I will say that fluorine atom, if you see, fluorine wants to take one electron, because if it takes one electron it will become octet configuration, like that, right? Even zinc, if it loses two electrons it will become completely outer fill electrons, maybe because of that or whatever. Zinc, I mean, not only that criteria, there are many criteria to have this ease. Please make a note. So zinc will donate electrons always. So zinc undergoes oxidation. Therefore, this electrode is named as anode, and oxidation half reaction is given here. Zinc solid is converting into zinc plus 2 ions and 2 electrons. Whereas onto the cathode, the half reaction is copper plus 2 ions accepting 2 electrons to convert it into copper solid. Solid means it is deposited onto this rod. Okay, solid you can see. Then the full net reaction of this cell, you add just addition of these two. So when you add these two reactions, the 2 electrons from product side and 2 electrons from the reactant side get cancelled, and you will get this net reaction of the cell. This is nothing but my redox reaction. Please, it is very simple to remember, identify, understand and identify. Remember this basic galvanic cell or voltaic cell or Daniel cell or electrochemical cell, because we can construct hundreds of galvanic cells or electrochemical cells by combination of different metals. See, copper, zinc you kept, zinc, nickel you can keep, copper, nickel you can keep, copper, silver, zinc, silver, many different combinations we can use and construct. So this is your electrochemical cell. I would like to show one video to understand more clearly. Okay. First, here salt bridge, I said no, salt bridge, in this gel will be present and KCl is there. So what is the use of it? For example, here all zinc plus 2 ions are increasing more. I mean, cations are increasing more. To neutralize it, Cl minus will move from here to here, the salt bridge to here. Whereas in this, potassium ions will move, because copper ions are continuously moving and going on to the copper rod electrode. Therefore, potassium ions can replace, I mean, to maintain the neutrality of these solutions. Okay. The same working of this cell you can find more clearly in this. Please make a note. Look at this redox reaction just from the YouTube only I have taken, just to understand more clearly. Uh, you can look at this. Here, zinc copper rod, when zinc rod is dipped. So this is our electrochemical cell. Just now I have shown. This is the No, this is the salt bridge where you can find here, you can see, and this is the metal wire where you can show on off switch there. And in salt bridge, you can find KCl or ammonium nitrate, whatever. They are using ammonium, therefore, they are taking this ammonium nitrate as solution. But we are using sulfate and KCl, it's okay. So now this is the switch. If you on, the electron flow will continue. If you off, I mean off means this is open, no connectivity. If you off, there is no electron flow. If you close this, that is on. Then it will show the flow of electrons. See here, this is on. Here electrons are moving from zinc rod to copper rod. Electrons are moving, and in this galvanometer, I said no, cerameter or galvanometer shows me the indicator. See here, zinc is converting into zinc plus 2 and electrons are going. How fast it is going, you can see. See, the electrons are coming here, right? The electrons are coming and copper is going towards that electrode, and thereby my copper plus 2 is converting into copper atoms. And here reduction half reaction, oxidation half reaction. This oxidation half reaction, and this is my reduction half reaction, right? As soon as the reaction undergo, we can make the following observations. What are the observations? You can see here, copper rod is changing its color. So copper is deposited onto it, right? Okay, another one I want to show you. You can find many number of videos, whichever is convenient to you, you can use. See here, zinc and copper. This is anode, this is cathode, and see the arrangement. See here, zinc, all zinc strip na. So zinc atoms he has written, whereas in the solution he has written zinc plus 2 and SO4 minus, right? And here he has written in this solution copper plus 2, whereas onto the strip copper sulfate minus 2 again, SO4 minus 2. Then this is the salt bridge which is represented here, Cl. NaCl they have taken, KCl we have taken, no, doesn't matter. See here. Now the electron started moving from this side to the right, and which also can be indicated by keeping a bulb. If you keep a bulb, it will blow, or if you keep galvanometer, it will indicate. So zinc is converting into zinc plus 2 and plus 2 electrons. That is, oxidation is taking place. See how he is showing 2 electrons are moving continuously. So zinc is moving 2 electrons, right? And whereas copper is taking 2 electrons there, right? Copper is taking 2 electrons, and look at here, see, taking 2 electrons, copper atoms are coming near to the electrode. Look at, see, many coppers here, copper is coming to the towards this, see here, copper, because 2 electrons are coming, see here, copper plus 2 is coming from here and attaching, right? And whereas here, see here, this green balls is coming here, because here zinc plus 2 atoms are increasing. That means positive ions are increasing. Therefore, negative ions are entering into it to make the neutrality. Electrical neutrality, the Cl minus are coming, right? So, the net reaction is this one. So, that is about my electrochemical cell. Hope you understood very well about this electrochemical cell. And this is what working of the cell till now I was discussing. Oxidation, reduction, overall net reaction of the cell, and the deflection in voltameter or galvanometer will indicate the potential difference between. So what is that potential? So standard electrode potential. Standard electrode potential is nothing but the potential difference between the electrode and the electrolyte. Till now we have seen that onto the one electrode, positive atoms are increasing, right? Because in plus 2, right? For example, in your electrochemical cell, well, electrons are Coming to the electrode, that means cathode. So electrons are coming to the cathode. So who are coming? Copper plus 2 ions are coming. I mean positive ions are coming at the surface of that rod, thereby showing two different ions. I mean positive, negative charge is here, positive charge is here. So this generate a potential called electrode potential. This is nothing but the potential difference between the electrode. This is my electrode and this is my electrolyte solution. So thereby the electrode potential is generated. See, onto the cathode, if it is electrode potential generated, I call it is to be reduction potential, because onto the cathode electrons are gained and converting into a solid metal, right? So this is a reduction potential. Onto the anode, what? Zinc plus 2 ions are there, so negative ions are coming here, right? So this is oxidation potential. Oxidation potential is nothing but losing of the two electrons. Therefore, this is called onto the anode, oxidation potential takes place. See, the tendency of the electrode to lose the electrons to get oxidized is called its oxidation potential, and the tendency of an electrode to gain the electrons or to get reduced is called reduction potential. That means every metal has its own oxidation and reduction potentials. For example, zinc you have taken, it has undergone oxidation, therefore oxidation potential, right? Copper have undergone reduction, therefore reduction potential you have taken, right? But generally, in general, oxidation potential is reverse to that of the reduction potential. For example, if an oxidation potential of your zinc is 0.76 volt, because it is measured in volts, electrode potential is measured in volts, it is 0.76, then its reduction potential will be minus 0.76 volt. You might get confused, ma'am, it's not undergoing reduction, then why is the reduction potential? May not be here. Maybe some with the other metals it will undergo reduction, then at that time its reduction potential will be minus 0.76. Okay, oxidation potential will be exactly reverse of reduction potential, or vice versa you can take, right? Any electrode can have its oxidation potential or reduction potential. Electrode means you can imagine all your metals, non-metals, whatever you are taking, right? Any element have its own potential, right? Okay. So when the concentration of all the species in a cell is 1 molar, if you maintain 1 molar concentration in all the electrolyte solutions, then we call the electrode potential as standard electrode potential. Now, again, half cells are two different: oxidation half cell and reduction half cell. So, oxidation half cell can be standard oxidation half cell and standard reduction potential, right? But according to IUPAC nomenclature, I mean convention, standard reduction potential are now considered to be standard electrode potential. Again, I repeat, any electrode can have oxidation potential and reduction potential. But according to IUPAC convention, we are using only standard reduction potentials as standard electrode potential. For example, what is the electrode potential of the zinc? If you ask me, definitely it must be 0.76 volt, I would say. I would not say that minus 0.76 volt, because its reduction potential is, sorry, zinc is, I will say that minus 0.76 volt. I will not say 0.76 because its reduction potential is minus 0.76. I'm not considering the oxidation potential. Okay. Standard reduction potentials are the standard electrode potentials. Okay. Then what is the cell potential? See here, half cells we said till now. If you combine both the half cells, then I call it to be a cell. Therefore, the difference between the potentials, I mean reduction potentials of the cathode and anode of a galvanic cell is called cell potential or electromotive force. Whatever all the potential generated in the cell, that means from the cathode, that is minus, to the anode, is called E cell. Sometimes it is given as E naught cell. Superscript naught also will be given E naught of the cell, because at standard temperature conditions, 1 molar conditions we are taking, right? and it is measured in volts. Now, the one representation of galvanic cell. Anode is written on the left side and the cathode is written on the right side. Okay. In a galvanic cell, here the electrode and electrolyte. This is my electrode, zinc electrode, and electrolyte is zinc sulfate. And how much is the concentration? 1 molar is the concentration. So both are separated by one slash or a line between them. And this is anode representation. This can be represented even by keeping the semicolons. Zinc, semicolon, zinc plus 2. Or because zinc plus 2 is nothing but zinc sulfate. Here, electrolyte only. Electrode and electrolyte. Electrolyte can be given as zinc plus 2 or zinc sulfate. And its concentration. Actually, this will be more convenient, but in writing a reaction, this is also convenient. So both okay. Now, cathode representation, electrolyte and the metal, that is copper. Here, copper plus 2. Copper plus 2 is nothing but copper sulfate, my electrolyte, 1 molar, and it is converting into copper rod, copper solid, therefore copper metal. This is exactly reverse to that of this, or else what is happening in the reaction is what we are writing. Zinc is converting into zinc plus 2, and copper is converting into copper plus 2 to copper, right? Here, either I can keep semicolon or I can keep one line to represent anode half reaction and cathode half reaction. But now I want to write full cell representation. So this is my full cell representation. Look at this, zinc, that means metal, electrolyte, and salt bridge. So this half cell reaction is separated by this half cell by keeping two vertical lines. Then electrolyte and metal. So right side should be cathode and left side should be anode. For this sake, actually, even in the electrochemical cell also, I have used onto the right side cathode dipped, right? And onto the left side only anode. I use it to write even only in this notation. So you have to practice writing the cell representation in this manner. By looking into this cell representation, you should understand what happened here. Zinc is converting into zinc plus 2. Copper plus 2 is converting into copper. Okay. Now, this is actually full. In this way also I can write, I said no. Instead of writing the full zinc sulfate, I can also show you zinc plus 2 and 1 molar. Its concentration has to be represented here. If it is not 1 molar also, you can show what is that concentration of that half cell. So oxidation half cell should be onto the left side, reduction half cell onto the right side. See here, copper sulfate, instead of writing CuSO4, I can write Cu plus 2 and its concentration. And this is nothing but reactants before products here. And change in state. This vertical line also indicates the change in state. Just now I said na, zinc has been converting into zinc plus 2. And this vertical line, two lines indicates that salt bridge indication. Okay. Then next we have to continue is electrochemical series. So the arrangement of elements in the ascending or descending order of their standard electrode potentials, that is nothing but reduction potential values, is called electrochemical series. I said no, all metals, non-metals, every element have its own electrode potential. So that in that oxidation electrode potential and reduction electrode potential both will be present. But I said IUPAC convention, we are using elements. Reduction potentials are considered as the standard electrode potentials. So if we arrange them in an order, see, some elements are not showing that much significant electrode potential, we will ignore it. So major important elements have placed, and in a table they have arranged in the increasing. See, increasing and decrease actually I have written because of your textbooks. In your CBSE textbook, he has written lithium is at the top. Actually, that is correct writing. Lithium element has to be written at the top and the fluorine at the last. But whereas in your state textbook, Telugu Academy book, he has written fluorine as the top and the lithium as the down. Therefore, I have written ascending and descending. Actually, ascending order we have to write. Okay, let me show this here. Here is the table. Here, first fluorine. Fluorine actually is taking 2 electrons and converting into 2 fluorides. So gain of electron is reduction. Here, all reductions only I have shown because reduction potentials only I am writing. Actually, lithium plus taking 1 electron converting into lithium is not happened because lithium wants to lose an electron. Because if potassium wants to lose an electron, you know, first year group elements and second year group elements, they want to lose electrons to convert into plus 2. That is oxidation they want to undergo. But I said reduction also can be possible. So I am writing reduction potentials only. Therefore, I have taken. And therefore, it is minus. Actually, lithium converting into lithium plus electrons is plus 3.05 is correct. That is its oxidation potential. But now, according to IUPAC, I want reduction potentials of all the elements. Therefore, reversing its number, I mean plus value is reversed to negative value. I have written minus 3.05 and arranged in this table and given to you. And these are called as your electrochemical series. Right? Look at this. Fluorine, its reduction value is 2.87. Therefore, its oxidation potential value will be what? Minus 2.87 volts. Right? Rm, chloride. So, chloride's reduction potential is 1.36, whereas oxidation potential will be minus 1.36. Right? And hydrogen's reduction potential is arbitrarily taken as 0 because one standard notation we should have. So these elements reduction potential is taken as 0, and thereby based on these elements more reduction or having more oxidation powers, they have arranged this. Okay, so here almost your non-metals have come here other than this Rm, platinum and all. Here fluorine, chlorine. So fluorine is undergoing most reduction. So it is undergoing most reduction, therefore it is called as good oxidizing agent. So in the periodic table, this is the strongest oxidizing agent, right? Whereas lithium is taking losing electron, actually taking electron oxidation reduction, right? Its reduction potential is very least. Therefore, it mostly undergoes oxidation. Therefore, this is the most reducing agent in the periodic table, right? See here, the arrows here indicates from top to bottom increases the strength of reducing agent, whereas from the bottom to top increases the strength of oxidizing nature, that means oxidizing agent. So top elements all wants to undergo reduction, that means gain of electrons. This bottom electrons elements all wants to undergo oxidation, that means loss of electrons. I mean they want to relieve the electrons. So this is what I have written here. So from the chart it is clear that fluorine has the maximum tendency to get reduced as F minus. Therefore, it is the strongest oxidizing agent where E naught of the fluorine is plus 2.87 volt. And whereas lithium want to undergo oxidation, that is lithium plus, and its reducing agent, and it is E naught is minus 3.05 volt. Okay, so in a construction of the cell, we generally take electrode with more potential values. Here, I don't want to confuse with more negative, more less value and all. Right? We know if we given two values, which is more in these two, this is only more. So this we want to consider as the cathode, fluorine. Whereas lithium we want to consider as anode because it is having the less potential value, right? Reduction potential only. Whenever I'm talking now potential means reduction potential only, right? And the E cell of the cell is again cathode minus anode. Very simply I can calculate one example for you here. See here, this is the E cell, I mean full reaction, net reaction of the cell, and where he has given zinc, I mean cathode is, I mean cathode means copper. Copper is 0.34 volts it seems, and zinc is minus 0.76 volt. Therefore, E cathode is 0.7, minus of minus will become plus. Altogether, it will be 1.1 volt for our copper zinc electrochemical cell. Please remember these values, so that other calculations you may not get confused. Okay, you can calculate for these two. I have given in the form of cell notation. Here galvanic cell notation, zinc is converting into zinc plus 2, its reduction potential value is this one, and nickel is converting into nickel plus 2 is converting into nickel, and its reduction potential is this. Here, if an EMF cell is going to be get negative, that cell is not existed. Here, this is EMF of the cell we are calculating. If unfortunately you get answer as negative, the cell cannot work out, right? We have to get positive values only. Whether it is possible or not, constructing a cell also we can calculate by writing this EMF of the cell, right? So these examples you can do, and you can show whether the cell can be constructed or not.